Consider this. At this very instant, absolutely everything, without exception, is engaged in a state of rotation. Our own planet Earth, for instance, performs a complete turn on its axis every 24 hours. And that, quite simply, is the reason we experience the familiar cycle of day and night. But our planet doesn't merely spin on its axis. It also embarks on a grand journey around the sun, a voyage that spans a full year. That particular curved path is precisely what we designate as an orbit. And the sun itself, it's hardly stationary. It's also engaged in an orbital dance around the very core of our galaxy. To complete merely one such colossal circuit, it demands a staggering 200 million years. And here's a thought: the entire galaxy itself, that colossal structure we inhabit, is also in a state of rotation. Imagine, if you can, billions upon billions of stars, every single one of them whirling in grand sweeping circles around that central core. Now, if you were to direct your gaze through a powerful telescope at other galaxies out there, what would you observe? They too are spinning, almost every single one, frequently coalescing into those magnificent spiral forms. Let's shift our perspective for a moment and turn our attention to the dynamics of our weather patterns. Those colossal hurricanes, for instance, they're spinning, and those fierce destructive tornadoes, they spin as well. Even that tiny whirlpool spiraling down your bathtub drain, it's spinning too. So all of this evidence brings us face to face with a rather profound question. Why then does it seem that everything is caught in this perpetual state of rotation? What makes this phenomenon of rotation so incredibly widespread across the entire universe? Why don't things just, proceed in nice, simple, straight lines? But hold on a moment, because here's an even more intriguing question to ponder. You've got planets circling the sun, moon circling planets, everything's constantly in motion around something else. So why then doesn't it all just smash right into one another? So let's take a closer look, shall we? Consider this. At this very moment, the moon is in perpetual motion around our Earth, constantly circling, always orbiting. What then prevents it from simply flying off into the boundless cosmos? But then the opposite puzzle, why doesn't it just plummet straight into Earth? And get this, it's actually moving at an astonishing clip, roughly 2,000 miles every single hour. So why this particular curved path? Why a circle specifically? Why doesn't it simply continue in a straight line, as objects naturally tend to do? Now here's the clever part. We have two distinct forces working at the very same time. The moon, by its very nature, wants to travel in a straight line. That's its fundamental inherent motion. But then Earth's gravity is constantly tugging at it, pulling it directly, relentlessly, towards our planet's very core. So what's happening is the moon is actually falling towards Earth, all the while it's also moving sideways. This fascinating combination of these two motions, the sideways and the falling, bends its path into a curve. And here's the magic. If its speed is just right, that curve elegantly, beautifully forms a perfect circle. So, you see, the moon is perpetually falling around Earth, but never, ever into it. This, my friends, is what we call an orbit, a continuous, endless state of falling that simply never quite lands. For billions of years, the moon has been performing this incredible cosmic ballet, always falling towards Earth, always missing, circling without end, never crashing, never drifting away. And guess what? The exact same astonishing phenomenon is happening with our Earth's journey around the sun. Right now, at this very moment, as I'm speaking to you, we are all, every single one of us, falling towards the sun. But here's the kicker. We're also hurtling sideways at an absolutely incredible 67,000 miles per hour. And that speed, precisely that speed, is what ensures that as we fall, the sun's gravitational tug bends our path into a perfect, beautiful circle. It's quite remarkable, isn't it, that we're orbiting instead of simply plummeting. What's truly fascinating is that every planet, without exception, acts in precisely this fashion. Consider Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, each one constantly pulled inward by the sun's gravity, yet simultaneously possessing a sideways velocity that keeps it perpetually circling. It's this exquisite balance, this tug-of-war between the inward attraction and the lateral momentum that forges those incredibly stable, nearly circular paths, enduring for eons. But now here's the profound question that truly baffles us. From where did that initial sideways impetus originate? Why does everything already have this inherent movement, this initial push, precisely at the moment it starts its fall towards a gravitational center? So, let's take a trip back, right to the absolute start. The cosmos, as we understand it, commenced with an immense, powerful burst. All matter was violently flung outward, away from its central point of origin. And that raw energy, in a remarkable cosmic alchemy, then coalesced into matter. Tiny particles started to emerge, gradually clumping together to form atoms, mostly hydrogen. These nascent atoms then scattered across the vastness of space, giving rise to immense gas clouds, stretching for light years, merely floating in the deep, dark void. Yet, these enormous clouds, it's important to note, weren't perfectly motionless. Indeed, absolutely nothing throughout the vast expanse of the cosmos ever achieves complete stillness. There's always some inherent movement, perhaps a nudge from a distant explosion, a gravitational tug from a denser area, fluctuations in temperature, shock waves from collapsing stars, or simply the ceaseless dance of random perturbations. And when all these influences converge, they collectively produce an unceasing state of flux. Thus, this immense gas cloud finds itself slowly meandering, with its myriad components each pursuing their own distinct trajectories. And here's the vital point. This cloud isn't a rigid, solid entity. It's simply diffuse gas. As a result, separate pockets within it can shift independently, some veering one direction, others another, some ascending, some descending, a truly tumultuous, uncoordinated dance. And it is precisely at this critical moment, this very turning point, that the force of gravity starts to make its presence felt. Imagine inside this cloud, any spot, even slightly more packed with matter, will naturally pull harder with gravity. What happens then? They start sucking in more gas, becoming even denser, and that, of course, just makes their gravitational grip even stronger. And there you have it, a runaway process, a feedback loop. The cloud starts to cave in, gently at first, but then it really picks up pace as gravity just won't quit, dragging all that material relentlessly toward the center. Yet as this grand collapse unfolds, something absolutely crucial, something profound starts to manifest. Now keep in mind, the different bits and pieces of this vast cloud aren't all heading the same way, are they? So as these fragments tumble inward, they bring all that pre-existing motion along for the ride. Some of that motion, quite naturally, is going to simply cancel itself right out. Think about it. A push to the left can be perfectly balanced by a push to the right. Similarly, an upward path can negate a downward one. But here's the trick. Not every last scrap of that motion actually manages to vanish. What's invariably left behind, you'll find, is always some overall spinning motion. Thus, the entire cloud, taken as one, ends up with a definite rotation. It could be minuscule, perhaps almost impossible to detect, but it is undeniably present. All right, now let's conjure up an image. An ice skater, gliding and twirling with elegance. Their arms are extended far out, and they're turning around rather slowly. But then pay close attention to what occurs the very moment they draw their arms in close. Suddenly they're whirling around faster. Oh, much, much faster, astonishingly faster. They didn't inject any fresh energy into the system. They certainly didn't push against anything, did they? All that happened was they brought their body's mass nearer to the axis of their spin. And the rotation, as if by magic, just automatically accelerates. This, my friends, is what we call the conservation of angular momentum, a principle so fundamental it underpins so much of what we understand about the physical world. You'll notice, won't you, that anything in a state of rotation exhibits this peculiar inclination to simply continue its spin. But now, for the truly intriguing bit, if that rotating mass contracts inward, drawing nearer to its core, its rotational velocity skyrockets. And our very own collapsing gas cloud, it's engaged in this exact phenomenon, you see. So as this cloud spirals inward, shrinking ever smaller, any initial gentle rotation it once held suddenly becomes astonishingly swift. That subtle, almost imperceptible turning, it transmutes into a furious, dizzying whirl. The cloud simply continues its rotation, gathering momentum, accelerating at an ever-increasing pace. But wait, there's an even more curious development. As it truly accelerates, something entirely different begins to manifest. It compresses itself, becoming remarkably flat. All that material, once diffused in every direction, is now pressed down into a mere 2 dimensions, coalescing into a flat, rotating disk. Let's consider, by way of illustration, a piece of pizza dough. You launch it into the air, imparting a vigorous spin. What precisely do you observe occurring? It promptly flattens, spreads out broadly, and transforms into a disk. That rotational motion propels the material outward, but exclusively along the flat plane in which it's turning. The dough ultimately becomes both flat and perfectly circular, and precisely this identical phenomenon manifests with our gas cloud. It compresses itself, thereby becoming a rotating disk. The material spreads out horizontally, driven by its spin, while simultaneously being squeezed thinner from its upper to lower surfaces. What remains then is a delicate rotating disk fashioned from gas and dust. And this, I assure you, isn't merely some isolated occurrence. This very process unfolds ubiquitously across the entire universe. Here's a curious fact. Any gas cloud that undergoes collapse unfailingly molds itself into a rotating disk. It's not a sometimes occurrence, nor a perhaps. It happens every single time, without fail. This particular behavior, you see, is intrinsically woven into the very fabric of physical laws. It's an unavoidable consequence, a direct result of those laws. A collapsing mass, even if it starts with just a tiny bit of rotation, automatically and inevitably transforms into a spinning disk. And what happens next? Gas begins to accumulate right at the very heart of this disk. A steadily increasing amount of material spirals relentlessly inward. This central region then becomes extraordinarily compressed, incredibly dense and intensely hot. The heat skyrockets, pressure intensifies dramatically, reaching temperatures of millions of degrees. Finally, the core reaches such an astonishing temperature that hydrogen atoms begin to fuse. It's at this precise moment that nuclear fusion genuinely springs to life. As hydrogen converts into helium, it unleashes a truly colossal amount of energy. And just like that, you see, a star is born. And this brand new star, it's spinning. That's an absolute necessity. Its rotational motion was simply inherited from the initial collapsing cloud. There's simply no escaping this reality. Our very own sun, you understand, came into existence in precisely this fashion. Visualize this. Some 4.5 billion years ago, a truly colossal gas cloud within our galaxy started its collapse, picking up speed as it contracted, ultimately flattening into a disk. Eventually, the central core achieved the critical temperature needed for fusion, and with that, our sun sprang to life, igniting brilliantly. And it's kept on spinning right up to today. A single turn takes about 25 days. But here's the thing, the disk didn't just vanish when the sun ignited. Instead, a wealth of material, gas and dust persisted, circling the nascent sun. Everything was still moving in those same circular paths, following the original cloud's spin. And this particular disk, we call it a protoplanetary disk. It's the very place where planets begin their existence. Now, over the course of millions of years, the tiny particles within this disk start to bump into each other. If these encounters are gentle, something remarkable happens. They stick. So dust grains latch onto other dust grains, gradually forming larger clusters. Then these growing clusters bump into still more clusters, fuse, and become even grander aggregations. And so, with agonizing slowness, these collections begin to swell. Dust grains morph into pebbles, pebbles into rocks, rocks into boulders, and eventually, boulders become mountains. These mountains then graduate into what we call planetesimals, essentially miniature planets. Finally, these planetesimals themselves crash together and coalesce, forming full-fledged planets. This entire grand process spans millions of years, but make no mistake, it absolutely occurs. And once this cosmic construction is complete, what do you have? Planets, gracefully orbiting a star. But now, let's get to the really crucial part. Every single planet, you see, was already in motion, already orbiting, long before it fully coalesced. Why? Because it was born within a rotating disk. The very particles that clung together to build that planet were already zipping sideways, already circling the sun. And when they finally merged, they simply carried that motion right along with them. That initial sideways motion, you ask? It was an intrinsic feature, a direct inheritance from the spinning disk itself. And that, my friends, is the precise reason why all 8 planets in our solar system embark on their journeys around the sun in one consistent direction. They certainly didn't arrive at a conscious decision to orbit in that particular manner. No, their path was simply dictated. Each of them sprang forth from that identical spinning disk, inheriting its initial rotation, its very orientation. Consider this. Mercury traces its orbit, then Venus, then Earth, Mars, Jupiter, Saturn, Uranus, Neptune, each faithfully circling in that very same direction, all adhering to the primordial spin of the disk from which they coalesced. Now imagine for a moment if these planets had materialized independently from entirely separate cosmic clouds. Their orbits would be utterly random, some spiraling clockwise, others counterclockwise, at various angles across distinct planes. What a mess. However, they did not emerge in isolation. Instead, they coalesced as a unified whole within a single disk born from one solitary collapsing cloud. Consequently, they all journey in concert, sharing the same orbital direction and occupying the same flat plane, much like the precise tracks on an old vinyl record. Now let's direct our gaze to the very plane within which they perform this grand celestial ballet. What do you observe? It's remarkably flat, indeed exceptionally so. Every single planet maintains its orbital trajectory within just a few degrees of that identical shared plane. And the underlying reason for this? Quite simply, they originated inside a flat disk. This primordial disk, though perhaps a few million miles in thickness, spanned billions of miles across, making it incredibly, astonishingly planar. Since the planets coalesced within that remarkably flat disk, it's only natural that their orbits would also be flat. Beyond their orbital journeys, the planets themselves also possess an intrinsic spin. Our own Earth, for instance, completes a full rotation once every single day. And Mars, quite surprisingly, also spins on its axis roughly once per day. A day on Jupiter lasts a mere 10 hours. Saturn, not far behind, spins in just 11 hours. They're all in a constant whirl, but why is that? It's for the very same reason everything else in the cosmos rotates. When planets were first forming, material from their surrounding disks spiraled in, imparting a rotational force. It wasn't perfectly symmetrical, leaving a residual spin. With the planet's growth, its rotation accelerated. It's that familiar principle again, the conservation of angular momentum. As its mass increased, the planet's rotational speed picked up. Once they began to spin, they just kept going. They're still spinning billions of years later, and fascinatingly, even moons originated in much the same fashion. As planets expanded sufficiently, some formed their own miniature disks of material, essentially tiny versions of the Sun's original protoplanetary disk, all orbiting the planet itself. This orbiting matter then collided, adhered, grew larger, and eventually coalesced into moons. Jupiter, for example, possesses scores of moons. Saturn, likewise, is orbited by dozens. Every single one orbits, moves laterally, and originated from those rotating disks encircling the planets. But our Earth's moon, it seems, probably came about in another way entirely. Most scientists propose a colossal impact event, where a body comparable in size to Mars collided with the early Earth. The impact was incredibly violent, launching immense quantities of debris into orbit around our planet. Imagine this material gathering together, shaping itself into a searing disk of vaporized stone, forever circling our brand new Earth. Over vast stretches of time, this incandescent disk gradually lost its heat. After innumerable impacts, these pieces stuck together, slowly assembling themselves into that familiar orb we now recognize as the Moon. Its birth story was quite unlike that of other cosmic companions, yet the fundamental result, remarkably, was precisely the same: a whirling disk, a steady spin, and a reliable path through space. Ever since that time, our Moon has diligently traced its path around our planet. Now, why does it rotate in the identical direction as Earth? Well, that's because it originated from the very same swirling remnants of our own world. But hold on, let's broaden our perspective, stretch it immensely, to those truly magnificent structures we call galaxies. Our home galaxy, the Milky Way itself, is a stunning spiral, a colossal spinning disk. Just picture it. Countless billions of stars, each and every one of them circling the central heart of the galaxy. Our Sun, for example, finds itself roughly halfway out from the galaxy's central hub. One complete circuit around the galactic center, that requires an astonishing 200 million years to accomplish. And don't think for a moment we're stationary. We're rocketing along at roughly 500,000 miles an hour, orbiting right alongside every other star in our immediate cosmic vicinity. So what's the fundamental reason for the galaxy's grand rotation? The explanation, rather remarkably, is precisely the same principle that causes everything else in the cosmos to spin. Envision this. It began as a collapsing cloud of gas, an absolutely immense structure stretching across millions of light years. At first, that cloud possessed a particular rotation, a very slow, almost imperceptible turning motion. However, as it yielded to the unyielding grasp of its own gravity and started to shrink, that rotational speed dramatically increased. It whirled with ever-increasing speed until the cloud spread thin, shaping itself into a clear, defined disk. And it was right inside this very spinning disk that stars first started to gather and ignite. And for countless billions of years thereafter, they have steadfastly followed their orbits around the galaxy's heart. So when we peer into distant galaxies, what do we find? This very same remarkable configuration. An overwhelming number of them reveal themselves as spirals, colossal spinning pinwheels of stars, each individual star perpetually in motion. However, not every galaxy takes on a spiral form. Some manifest as ellipticals, resembling more indistinct, shapeless clouds, seemingly lacking intricate organization. But here's where it gets truly intriguing. Even these apparently less structured cosmic entities nonetheless display a fundamental rotation. Indeed, the stars within them are in constant flux, orbiting their gravitational core, albeit perhaps along less orderly trajectories. Yet the collective rotational movement is unmistakably there. What accounts for this universal spin? The answer, my friends, lies in gravity, which, as you know, is just as universally present. And whenever gravity commences its inward pull on matter, whenever a cosmic collapse unfolds, any initial minute movement becomes extraordinarily magnified. What began as barely perceptible turns rapidly intensifies into colossal swirling motions. From a sluggish drift, it swiftly picks up speed, transforming into a swift, powerful spin. This, you understand, is an unavoidable outcome. It is the bedrock laws of physics that orchestrate this entire process. And this precisely is the reason our universe exhibits such intricate structure, why it isn't simply a homogeneous, indistinct haze of gas spread evenly throughout the emptiness. The explanation you'll find is that rotation actively thwarts a complete, unrestrained implosion. While objects are certainly drawn inward, yes, they simultaneously carry a vital lateral momentum. It is this very side-to-side movement, this essential tangential impetus, that stops them from utterly collapsing into one singular compact mass. Instead, they establish themselves in enduring, stable orbital paths. They spread out into vast disks, structure emerges, order flourishes, galaxies, stars, planets, all born from the foundational interplay of gravity and rotation. Picture a cosmos utterly lacking rotation. Everything would merely plunge directly inward, undergoing a complete collapse. Immense clouds of gas would condense into undifferentiated compact spheres. No graceful disks, no planets orbiting suns, no complex solar systems. Just enormous masses of gas and stars, probably providing no sanctuary for life to arise, no steady foundations, no worlds with firm ground, nothing lasting or secure. In the end, our very presence here depends entirely on the universe's ceaseless, wondrous rotation. All right, let's circle back to that crashing question. Why precisely do planets not simply plunge into the sun? And what about our own moon? Why doesn't it ever smash into Earth? If gravity constantly tugs them closer, why do they never, in the end, collide? It's all thanks to that sideways movement, that orbital speed. The moon, believe it or not, is actually falling towards Earth right this instant. Gravity's pull relentless. But here's the trick. The moon is also hurtling sideways at roughly 2,000 miles per hour. That's quick enough that as it tumbles towards Earth, our planet's curved surface simply falls away beneath it. So the moon perpetually misses its target, Earth. It falls around Earth, you see, never into it. Just drop something, anything, and what happens? It falls straight down. That's because it possesses no sideways momentum. It simply drops. But now imagine you throw something sideways while it's falling. What then? It traces a curved trajectory, simultaneously falling and moving horizontally. This combination of motions creates that distinctive curve. Now hurl it faster with more force. The curve stretches out, becoming flatter. Launch it with enough speed, and that curve will perfectly match the Earth's own curvature. The object then falls around Earth, you see, never into it, and that precisely is an orbit. The moon then is travelling sideways at exactly the correct velocity, a speed sufficient for its curving descent path to perfectly align with Earth's own rounded surface. So it never draws nearer, never crashes, but simply circles endlessly. Imagine if the moon's speed were to slow down even a tiny bit. It would start a deadly inward spiral, drawing ever closer to Earth until it finally smashed into us. Yet it travels at just the right velocity, perfectly balanced to maintain its orbital path. The constant downward pull of gravity and its sideways motion achieve a beautiful, delicate equilibrium. And this very same principle, this exact idea, holds true for our Earth and the Sun. At this precise moment, we are in a perpetual state of falling towards the Sun. While gravity exerts an unceasing tug upon us, we are simultaneously hurtling sideways at an astonishing 67,000 miles per hour. This velocity is so perfectly tuned that as we descend towards the Sun, its colossal surface continually curves away beneath us. We just keep missing it forever. Consequently, we orbit the Sun rather than plunging directly into its fiery depths. Should Earth's pace slacken, we would commence a fiery spiral descent into the Sun, growing progressively hotter until we were utterly consumed. Conversely, accelerate Earth's motion, and we would be flung outwards into the vast emptiness of deep space, experiencing an ever-decreasing temperature until we froze solid. We occupy the precise midpoint, a flawless equilibrium, perfectly suited for a sustained and stable orbit. This delicate balance isn't unique to us. It governs every planet, every moon, every satellite, indeed every single object revolving around another. Each one is in a state of perpetual descent, constantly drawn by gravity, yet simultaneously moving laterally with just enough speed to perpetually miss its target, thus achieving orbit instead of collision. Furthermore, these orbital paths are remarkably stable, truly astonishingly so. Our Earth has faithfully traced its path around the Sun for an astounding 4.5 billion years. Maintaining the identical orbit, distance, and velocity, it has neither plunged into the Sun nor drifted off into the cosmos. It simply keeps circling without end. Similarly, the Moon has circled Earth for more than 4 billion years, adhering to the very same trajectory. While the Moon is indeed very gradually receding due to tidal forces, this drift occurs at an almost imperceptible pace. An orbit, it turns out, is an astonishingly stable thing. But what exactly grants these orbits their astonishing, unwavering stability? How do they manage to persist for eons, for billions of years, hardly straying from their courses? The straightforward answer, you see, is that there's simply nothing out there to slow them down. Because space, my friends, is a colossal void, an almost perfect vacuum, utterly free of air, friction, or any form of drag. Consequently, when an object travels through this immense emptiness, there's absolutely nothing to stop its motion. Its journey then continues on forever. Energy stays conserved, momentum stays conserved, and that's why these orbits just keep going. Now, down here on our planet, it's quite another matter. Everything eventually comes to a stop. Thanks to friction, air drag, and things constantly rubbing against each other, energy converts into heat and movement simply dies out. But out there among the stars, none of these effects ever happen. Heavenly bodies just keep moving, endlessly circling, unless, that is, they happen to smash into something. Truly, this is the universe's most basic intrinsic condition. Once something starts spinning, it just keeps on spinning. And once it begins to orbit, that orbit will simply carry on. The motion, you understand, is genuinely unending. Even right here on Earth, we can spot a similar rotational phenomenon, the magnificent swirl of a hurricane. And the cause? It's because our own world is perpetually turning. Our Earth makes one complete spin day in and day out. As a result, different parts of our globe are moving at distinct speeds. Just think about it. The Earth's equator is hurtling through space at approximately 1,000 miles per hour. Yet as you approach the poles, that speed significantly diminishes. Thus, air masses near the equator are hurtling along, while those closer to the poles are barely creeping. Now, imagine air currents migrating from one latitude to another. They're passing over terrain, spinning at an entirely different rate. This causes the air to swerve, to bend its path, and to begin a fascinating rotation. And what we're witnessing here is precisely what we term the Coriolis effect. It's the very reason hurricanes in the northern hemisphere swirl counterclockwise, yet in the southern hemisphere they spin clockwise. Now let's introduce some warmth, specifically from the balmy ocean waters. That warm water then vaporizes, ascends skyward, and in doing so generates a region of lower atmospheric pressure. Naturally, more air then streams in to fill that void. And remember, that incoming air is already rotating. This rotation doesn't just stay chaotic, it begins to coalesce, organizing itself into a distinct spiral. With additional heat, we inject even more energy into the system. And what happens? That magnificent spiral begins to whirl with increasing velocity. Behold the hurricane, a colossal swirling tempest, its winds howling at over 100 miles per hour. Now let's consider tornadoes. Their formation surprisingly follows a similar blueprint. Within thunderstorms, we find incredibly potent updrafts, columns of air surging skyward. But here's the trick. If the wind speed varies significantly at different altitudes, that rising column of air begins to twist and rotate. As this column stretches upward, becoming thinner, a fundamental principle of physics takes over, the conservation of angular momentum. And as it stretches, it spins faster, much, much faster, a truly astonishing acceleration. Consider a tornado, a violently rotating column of air, its winds exceeding 200 miles per hour. Just watch the water spiraling down your drain. It's a vivid demonstration of this very principle. A mere whisper of a disturbance is often enough to set off a spin, and once that turning begins, it doesn't stop. In fact, it intensifies as the water spirals relentlessly downward. This is the identical principle at work, you see. Everything spins because the universe itself began with an intrinsic motion, which gravity then dramatically amplified. Nature, in its remarkable way, takes these minute chaotic movements and sculpts them into coherent, organized rotation. It's a profound process, one that molds initial disorder into a discernible, elegant structure. What started as humble, modest rotations eventually blossomed into vast, sweeping movements. This fundamental pattern, you'll find, repeats itself across every conceivable scale. Consider tiny clouds of gas. As they collapse under their own immense weight, they coalesce into brilliantly rotating stars. Likewise, colossal nebulae of gas undergo a similar collapse, giving birth to entire spinning galaxies, and from the swirling disks of gas that encircle nascent stars, planets eventually materialize, settling into their predictable orbits. The fundamental physics, you see, remains utterly constant, invariably yielding these identical outcomes. This grand narrative, in fact, stretches all the way back to the very dawn of cosmic time. In the nascent universe, motion was ubiquitous, teeming with random fluctuations and minute disparities in its initial movements. And those initial stirrings, they never, ever ceased. Instead, they expanded, were dramatically magnified by the relentless force of gravity, and coalesced into the magnificent rotating structures that populate our skies today. Simply direct your gaze skyward. Every single star you behold is perpetually engaged in a constant, mesmerizing spin, and each planet circling those stars is ceaselessly following its orbital path. Every galaxy you observe is in a state of magnificent rotation, and all of them are interconnected by one remarkably straightforward, unifying principle. This spin we're talking about, it's a quantity that's always conserved. When things collapse, that spin gets dramatically amplified, and it's this very rotation that sculpts the universe, creating its structures. Right now, you're standing on a planet that's perpetually spinning, and that planet, in turn, is circling a star that's also rotating. And that star, it's orbiting within a vast spinning galaxy, a galaxy that coalesced from material originating in spinning gas clouds. This fundamental rotation, you see, stretches all the way back to the very beginning. And that's the profound reason everything spins. Not because something's constantly pushing it, but because once that motion began, nothing ever managed to stop it. And then gravity stepped in, intensifying that spin, transforming tiny random jitters into magnificent spirals and refining chaotic drifts into elegant circular orbits. This spin, you see, is utterly fundamental, intrinsically woven into the very fabric of the cosmos, evident in everything from the smallest whirlpool to the largest galaxy. The pattern is identical, the physics precisely the same.